No. These are what the sort of the rules are here, okay? So those are two triangles. Neither of them are actually triangles because they look more like TVs, but X in the top. What they're saying is these two triangles are the same. If I tell you that this side on the left if I say the triangles look like that, 6, 7, 8, 6, 7, 8, they would have to be the same. Why would they? Because we said they have to have the same sides and the same angles. Why do I not need to worry about the angles in this case? Because this is something to start thinking about. Okay? Yeah, no? Sort of. Not really isosceles. Not sort of, but not really. Okay? Think with, assume you're using your arms. I like using arms for triangles, okay? If I know this arm's 6 and this arm's 7, and I know the distance between them has to be 8, how many ways can that happen? One, right? It's not like if I change the angle like this, it's going to be more than 8. If I make the angle less than that, it's going to be less than 8, right? So there's only one possible way I can have one arm at 6, one arm at 7 have a distance of 8. Okay, there's only one possible way, okay? And that's what we're saying, and that works all the way around. So that's a minimum. If all the sides are the same on two triangles, then they're going to be congruent. Okay. Number 2. And we'll look through this stuff fast, okay? This is only a minor, we're going to say if AB equals XY and BC equals YZ and angle B equals angle Y. This is SAS. Hey, that's an X, sorry. That's an L, that's sort of an angle. So what I mean for this is, and I'll get out of the way here in a sec, there's A, there's B, there's C. There's a theta, there's 5, there's 6. Those have to be the same triangle. If you have two arms and an angle, there's only one triangle that can be made. Okay? And that's the logic behind it there. Now, the question I have to ask, sorry, I know I'm going too quick. I'll take a pause here. This is one of these things we have to get through the congruence and the similarity today. This is a fundamental concept you need for the rest of this, okay? Because what we're doing in this unit is we're using smaller models of triangles to make predictions of bigger things. Okay, yes. Yes. All right, let's say I don't have that theta in there. Let's just say I need a 5 and a 6 for my two arm lengths. Are the two triangles going to be congruent necessarily? Is it possible if I just know this is 5 and this is 6, is it possible to make two triangles? Stay awake, guys, stay awake, please. Is it possible? Let's draw on the board here. There's a 5, there's a 6. Is there only one triangle that can be made? Can anyone think of a different triangle? Yes. What would it be? Go ahead. Yeah, this is another triangle, right? Right, here's another one. Okay? So see what I mean? That angle has to be fixed in the middle. You see what I'm doing there, right? So the angle has to be fixed in the middle, or else, I just said good comment there. The length of the bottom will change all the time. So that's why you need that fixed angle. I have one more of these, and we'll get to one or two examples here. Last one is going to be number 3. We're going to say if angle B equals angle Y, angle C equals angle Z, and BC equals YZ. This is ASA congruence, which is angle, side angle. Okay, so if I have 40, 70, and 10, have to be the same triangles, because if the angles are fixed, you can't move those arms, right? So they'll have to be the same triangles. Now, these three conditions that we did, side, 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 angle, those are three good things to probably know. What it'll be, there'll be one small question of this on your test, all right? And I'll do a few examples here in a second to show how they work. Yes? Yes, sorry. Oh, I'm sorry, I'm a messy thing. I got too excited.
I thought I was just saying.
No, it's okay, it's not too wide, that's why I said, sorry. So that should be, thank you. Oh, I'm sorry. All right, so I'm going to slow down here. I'm going to hit pause in the video so everyone can fix their notes. Okay, yeah, so obviously Mr. Sadler's a messy print. This is a heavy definition day. This is a heavy definition day on the first day. We'll get to work examples a lot more. So today we're dealing with similar triangles. And please put a star beside this, okay? This concept of similar triangles is, as I keep saying, the foundation of math, okay? We're going to say the expressions. Can I please go here, guys? We're going to say the expression. I'll use DEF this time, okay? Okay, so it says triangle ABC is squiggly line and DEF. It means that triangle ABC is similar to triangle DEF. Okay?
Wait, so the squiggly means similar?
Yes, squiggly means similar, and equals. Just wait. And equals with a squiggly is congruent. A squiggly is going to be similar. Okay. All right. Okay. So what this means for us is, I'm going to draw two triangles here right now. There's A, there's B, there's C. There's a theta, there's a beta, and there's an omega. And there's a little one called DEF. There's a beta, there's an omega, and there's a theta. So for similar triangles, as you can see, their angles are the same, but it's just a smaller version of it. Okay. So we're going to say side AB is in the same, these are all in the same proportion. So what I'm saying for this is they have to be in the same proportion. So what that would mean is if I can like divide this entire triangle by 2, right? Every side would be divided by 2. That's what I'm saying. Each triangle is in the same proportion then, or each side's in the same proportion to one another. And again, it has to be, if the angles are the same and I cut one in half, then they'd all have to be cut in half to keep the same, just keep the angles working the same way. Okay, trig does get more exciting. Stay with me here, okay? Okay, for this, okay? So these are just fundamental things you need to know, all right? Condition for similarity is going to be it's going to be SSS, excuse me, similarity. which means that AB over DB equals BC over BF equals AC over DF. Just bear with me here and we'll go through this. I know this is all just textbook stuff. We're done with the notes as of right now. Okay, here we go. Ready? Example one. Ready for some examples finally? Finally, we'll get some examples. Okay. It's 13, not a B. That's a 13, not a B. Thank you, though, for pointing that out. Just wait, just wait. Okay, so it says prove these triangles are similar. In this textbook and in this unit, we're very, very concerned that things are going to have to be similar, okay? Because that's you have to actually use them, so we'll have to prove them. Yes? So the way we're going to do this, we're going to do this by, since we have no angles here, the two ways to prove that things are similar is if you know the angles are the same or the proportions are the same. Why can I not prove that these triangles are going to have, the angles are going to be the same? There's no angles, okay? Eventually in this course we'll be able to solve the angles here, but not today. Okay, so I have to prove similarity because of proportions. Yes? Yeah, go ahead.
The sides on the bigger one are 3 times the numbers on the smaller
Very good.
one.
So the way I would actually write that, I'd say, well, 13 goes to 39, and then 14 goes to 42, and then 15 goes to 45. Oops. So that's all 130 equals 130 equals 130. Simple as that. Therefore, SSS similarity. Okay, so we got the idea of that. Again, so we've picked, Emily saw correctly. Again, it's just timesing by 3 to get to the right-hand side of the triangle. All right, example 2. How are we doing for the video? Let's take a pause. Let's say pause in the video here for a second.